This is our introductory lecture to DC circuits. The first thing we're going to talk about are the components that make up DC circuits. And the first topic that I want to talk about is this thing called current. Current, the symbol that we use for current is I. Current is the flow of electrical charges. And so if we have a current carrying wire, we know there are a bunch of electrons that are flowing through this wire. And once they get moving, the current is going to be defined as the number of charges that pass through a given area in a certain time period. And so I is defined as the number of charges per unit time. It's kind of like the traffic cop sitting and counting the number of cars that go by in a certain time period. The SI unit for current is going to be the amps, A. Q is going to be the amount of charge, and T is our time period. This problem states a steady current of 2.5 amps flows in a wire for 4 minutes. How much charge passes through any point in the circuit? Our variables here, our current I is going to be 2.5 amps. Our time period is 4 minutes. Can't be in minutes, we need to be in seconds, so we need to convert that. And so when we convert minutes to seconds, we get... Yeah, I'm doing this on my calculator because I'm that lazy. 240 seconds. So our I is going to equal to Q over T, as Mr. Shirley says, I quit! And so 2.5 is going to equal the number of charge carriables times 240. So when we do this math, we get the number of Qs, the number of charge particles, to be 600, and of course charge is measured in coulombs. If we wanted to convert that to electrons, we need to know the conversion factor from electrons to charge. Hopefully you remember that one electron has a value of 1.6 times 10 to the minus 19 coulombs. So when we do this, we're going to start off with 600 coulombs. 1.6 times 10 to the minus 19 coulombs in one electron. And so we just need to divide, and we are going to get a huge number, such as 3.75 times 10 to the 21st electrons. So when we have current flowing, there is lots of electrons moving. In order to have current flowing, there must be some things that are connected and moving along. And so what we need to look at is we need to look at this picture and determine what is wrong with this one. Hopefully that you can see that both ends of the battery are not connected, so we would have to extend that in order to have a current. Again, that's the same thing with this one. One of the ends needs to be connected to the positive terminal as well as the negative terminal. And this one should be good because we have a potential difference source, the battery, we have a resistor, the light bulb, and we have a wire that connects this. Once this is all connected, we will have current flowing through the circuit. We know in true life, or we should know, that electrons are our actual charge carriers. If this was the case, electrons should go from a lower potential, the negative terminal, to the higher potential, the positive terminal. However, Ben Franklin decided it was positive charges that carried the charge, so he decided that current flows from the positive to the negative terminal. This is what we use today, and we call this conventional current. Okay, so what does this mean in terms of you? Conventional current means that the electrons are going to flow from the positive. Actually, it's not going to be electrons, it's going to be positive charge carriers are going to flow from the positive to the negative. And we know in real life it's really opposite, but for all the problems that we work, conventional current is going to go from the positive to the negative terminal. Our granddaddy of them all equation in terms of the second semester. The first semester it was F equals ma. In the second semester it's going to be Ohm's law. Ohm's law relates potential difference, current, and resistance into the term Ver. V is going to be the potential difference in volts, I is the current in amps, and R is the resistance in ohms. The SI unit for resistance is that funky looking symbol right there, called omega, also known as an ohm. A small flashing bulb draws 300 milliamps from a 1.5 battery. What is the resistance of the bulb? Again, pretty easy here. Look what that is. That's my I. 300 milliamps. Can't be in milliamps. We need to be in amps. Milliamps to amps. We're going to plug a times 10 to the minus 3 at the end of that. Our voltage is 1.5 volts, and we're looking for resistance. V equals IR is our equation. 1.5 is going to equal to 300 times 10 to the minus 3 times this resistance R. And so when we plug this into our calculator, we are going to get a value of 5 ohms. If the voltage is dropped to 1.2 volts, how is it going to change? Once you have that value of that resistance, that is what it is. That is built to have that type of resistance. So we're going to plug it into V equals IR. My new volts is 1.2. I'm solving for my I, and this is going to be 5. So 1.2 divided by 5 gives me a current of 0.24 amps there. The next thing I want to talk about is a resistor, R. A resistor is any device that resists the flow of electrons. For you, anything that we plug in is going to be a resistor. The TV that's on right now, my cell phone is a resistor. The clock is a resistor. Anything that uses electrical potential energy will be a resistor. This didn't show up. We're going to use the symbol this. Our SI unit is going to be the ohm, and I'm lazy. It's going to look like this. It's going to look like this. But if I type it up, it really looks like that omega sign like there. Different resistors are rated different ways, and so you need to be able to identify what's going to happen with that resistor. And remember, resistor, anything that resists the flow of electrical charges. So let's look at this wire. If our length is a long wire, it's going to have a high resistance because there's more opportunity for those electrons to get stuck. Short wire will have least resistance. Cross-sectional area. Think about how fat or how skinny that wire is. One of the things that I thoroughly enjoy doing the day after Thanksgiving is we go shopping at 2 a.m. in the morning. As we're standing in line waiting to get into Kohl's, there's 300 of my closest friends in there. As they open up the door, though, they just open up one single door. One single door means there's 5,000 people trying to get in at once. There's going to be resistance. The big fat doors, if they open all the doors, everybody can get through, and so that will not have as great as resistance as that skinny wire. The type of material also has to do with resistance. Aluminum has more resistance than copper. If we could afford it, we would build all of our electrical wires out of gold because it has an extremely low resistance. It would not be financially feasible, although now with copper being so expensive, it's not feasible to build out of copper either. Temperature also has to do with resistance. A low temperature versus a high temperature. Think about what temperature is. High temperature means those molecules are going to wiggle, jiggle, wiggle around more. So as they wiggle and jiggle around more, they have greater opportunity to get stuck, so they will have a higher resistance. If we look at these first three things, there is an equation that you need to know for resistance. And this is what it is. Resistance of a wire is equal to this constant, L over A. This rho value is the resistivity of the material. It's going to be a specific value. L is going to be the length of the resistor, and A will be the area of the resistor. Again, both of those need to be in meters. Several different AP problems draws a bunch of different resistors, and it asks which one has the greatest resistance. And every once in a while you'll have to apply into this formula. They love to say, if the radius doubles, what happens to the resistance? And so make sure you know how to apply that. You'll have some practice on some internet homework with using this equation. Suppose you want to connect your stereo to remote speakers. If each wire must be 2 meters long, what diameter of the copper wire should be to keep your resistance less than 0.1 ohms per wire? The constant for copper is given as well. The length of the wire is going to be 20 meters. We have a resistance of 0.10 ohms. we have this value of 1.68 times 10 to the minus 8. And what are we looking for? We're looking for diameter. So I'm going to solve for area first of all. The formula, resistance equals RL over A. And so we're going to have 1.68 times 10 to the minus 8 times the length of our wire, which is 20 meters, divided by our area, which we don't know, and that's going to equal to 0.10. As I do this math in my calculator, it will give me the value of the area. However, I don't want the value of the area, and if I got this math right, which 2, 3, 4, 5, 6, I want to calculate then the diameter. I can say that area is going to equal to pi r squared, and divide that answer by pi, and then take the square root. Gives me a radius of 0.0010 meters. If the current in each speaker is to reach 40 amps, what is the voltage drop across each wire? We will use V equals IR. We're looking for that potential drop. The current I is 4 amps. The resistance is 0.10. And so when we do that math, we get a potential difference of 0.4 volts. Next one's tricky. Take a few minutes to read it, see if you can figure it out. Love the conceptual questions here. It says a wire of resistance R is starched, how about stretched, uniformly until it's twice its original length. What is going to happen to its resistance? Okay, so if we look at this formula, it seems pretty obvious that my length is going to double. But what happens to our area? If I stretch it to twice its original length, is my area going to be the same as the wire? Hopefully you can see that the area is going to be smaller, and so we can't tell what's going to happen here because we know the area is going to be affected. We just don't know by how much. The next thing we're going to talk about is this unit called power. Power, of course, is the rate at which energy is transferred. Our SI unit for power is the watts. Your light bulbs are rated in power. It's how much energy per unit time they give off. Again, power, energy over time. And we can rearrange this different ways, but here is the main equation. P equals IV. If we know P equals IV and V equals IR, how about V equals IR? We can substitute this in 1,000 different ways to get these equations right here. Be familiar with them because depending upon what stays constant is what you will use. You'll use this way when I doesn't change. You're going to use this equation when V doesn't change. And so just depending upon what you're given will determine which equation for power you will use. Calculate the resistance of a 40-watt automobile headlight designed for 12-volt battery. Power, going to be 40 watts. The potential, 12 volts. I'm looking for the resistance. Which equation has those variables associated with it? Hopefully you can see. Power is going to equal to V squared over R. And so we will plug it into the equation and be able to solve that for R. When I do the math, I get 0.36 ohms if I did it right. Nope, that time I got 3.6. So let me do it one last time to see if I can do this right or not. It is 3.6. 3.6 ohms is my answer there. Last little bit, just about done. The electrical energy. Electrical energy is the energy that you pay for from the electric company. The electric company, the rate is given in kilowatt hours. And so to calculate electrical energy cost, if I want to know how much it costs, I'm going to take my power, but notice my units of power needs to be in kilowatts. I'm going to multiply it by my time, which is in hours, as well as the rate provided by the power company. I think I've told you the story last year, but I'll tell you again this year in case you didn't have me. One of the things that I hate when I go home to visit my parents is that we always get griped at. Do you know how much the electricity bill goes up when you come? Do you not know how to turn off the lights? Yes, I get it heard all the time. It drives me absolutely insane. And so one day I took my parents and I calculated how much it cost to run a 100-watt light bulb for 24 hours. How much is it actually costing them? You know what? We'll stay the weekend. We'll stay a whole 72 hours. It's a long weekend. We went down to my parents. Long weekend. Okay, how much does it cost? So the cost is going to be the power. The power is 100 watts. Divide that by 1,000 because we need to be kilowatts. So that's going to be 0.1. Times our time, 72 hours. And the rate, we'll go ahead and use this rate. That's a little cheap. It's a little bit more expensive now, but 0.015 per kilowatt hour. And so when I multiply this out, and yeah, I've shown my parents this. Do you think they care? No. You know how much it costs to leave that stupid light on for a whole 3 whole days? 3 whole days. Yeah, less than $1, 0.75 cents. It's not me that makes their electricity bill goes up. It's that they keep it set at 65 during the summertime is why their electricity is so high. But that's a whole nother story. Alright, let's work this problem. Electric heater, 15 amps on a 120 volt line. How much power does it use to cost for 30 days if it's on 3 hours per day and it charges 0.15 cents per kilowatt hour? Again, if we plug into our formula, I need to know my power. I'm not given power. I'm given the current, 15 amps, and the potential, 120 volts. And so I'll have to do power equals I times V. And I can use this equation to calculate my power. When I do that, I get 1,800 watts. And so as I'm calculating my cost, I need to divide that by 1,000 because it needs to be in kilowatts. It's going to operate 3 hours per day, and 3 hours per day for 30 days. So I'm going to multiply that again by 30. And the cost is $0.015. And so when I do that math, I get a cost here of $17.01 to run that. One of the projects that I had to do a couple of years ago, or made my kids do, is actually look up the rate of what their power company provides. Kind of surprising on what the different rates are. So if you get bored, ask your mom and daddy what they pay for electrical energy costs. Get the little electric bill out and see what that is. Lightning is a spectacular form of electrical current. There is much variation in lightning bolts, but it can typically transfer 10 to the 9 joules of energy across a potential difference of 5 times 10 to the 7 volts for about 0.2 seconds. Estimate the total amount of charge transferred by the current and the average power over the 0.2 seconds. Okay, so how are we going to solve this problem? Estimate the total amount of charge if I'm given energy, 1 times 10 to the 9 joules. I'm giving potential, and I'm looking for charge, Q. Can you figure it out? V is the potential energy per unit charge. And so when I do this math, I'm going to have 1 times 10 to the 9th divided by my volts, which is 5 times 10 to the 7th. And again, I could probably do this in my head faster than I could stick it into my calculator, but I'm afraid I'll make a stupid mistake. And so I got Q to be 20 coulombs. Estimate the current. Well, once I have charge, I can say I equals Q over T. So 20 divided by 0.2 will give me my I. And that provides me with 100 amps. Wow. And then calculate the power. Power is going to be I times V. So I'm going to have 100 times that voltage, which is 5 times 10 to the 7th. And that is a heck of a lot of power being produced. Unfortunately, it's for a super short period of time, but I get 5 times 10 to the 9th watts produced. I think at this time we're going to break it off, and we will continue with this later.